Okay, so this problem says the following, okay. Well, it's about domino pieces, so let's see what it's all about. So let's say problem 3. Okay, so we have some domino pieces, you know domino pieces, right? Okay, something like this. Dum, 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 dum. Well, you can Google on YouTube. Domino pieces. Okay, so they start falling. We have very many of them, and we want to say something about the speed of falling, provided we know the dimensions of these things, right? So the spacing in between them, okay, let's use a different color here. All right, so here we have, okay, this is D, and then the thickness is tau, and then the height is h of this one of this piece, okay? And then you know how if we kick one and then they start falling one onto another. Blah, 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 blah. I might put a video in, you know, so blah, 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 blah. Okay, so what they want from us, okay, they want that somehow to show that the speed of falling, or yeah, the size of the velocity that is falling, you know, is something that looks like V would be the falling speed, let's say. Well, it's not, yeah, okay. It's not really the speed of falling, it's the speed of toppling over, right? You know, so yeah, okay. So speed of toppling. Okay. So this one, they say it should be something that depends on the gravitational constant, gravitational acceleration, okay? Then on h, the height of one of these pieces, and then there is a function of d over h and tau over h, okay? So show that v can be expressed in this way, where g is the gravitational acceleration, okay? And the rest you kind of know, okay? So dh tau. And as a fun part would be like, okay, so if the velocity on Earth is, I don't know, so let's say is 1 meter per 10 seconds, right? Something like that, let's say, or 1 meter per 5 seconds. What would be the same, what would be the velocity, the speed of toppling over, right? If we're on the moon, right? So on the moon, the gravitational acceleration is 6 times roughly 1/6 from here. So we could actually compute that, huh? It'd be fun. Anyhow, so problem in hand. Okay, so what do we have to do? Okay, so we're going to assume, so solution if you want. Okay, we assume there is a homogeneous law that combines everything together. And here I did the computation already, so let's keep the order that I used there. H, tau, D, G, and V equals 0, okay? And now what we have to do, we have to set up the fundamental units and the powers and get to the linear system and see how many independent variables we have and express them, and probably, you know, this would be the independent variables. And a third one will have 3, and the third one will be this v squared over gh or something. I'm just jumping, but okay, we'll take it one by one. So we have the measures, right? The units of this thing. So this is in length. This is in length. This is in length. Yeah, okay. And this is acceleration, right? So it's meter per second squared, right? So it's length time at -2. And finally, this is velocity. So it's meter per second if you want. So it's length time at -1. And my habit, and I advise you to do this, it's just nice to see. So the fundamental units. Okay, we have length and time. So there are just 2, whereas we have 5 variables. Okay, so now we're going to combine them. So we know that each one, so for each one, you know, there should be a power. I'm going to write it directly. And then for the third one, L, T at -2 at D, and then L, T at -1 at E. So all this should be L at 0, and then T at 0. And then we combine them, so we'll have L at power A plus B plus C plus D plus E, and then T at power -2D minus E. So all this stuff should be L at 0, T at 0. Yeah, okay. So we end up with a system, right? So this guy has to be 0. And this guy has to be 0. Right? So I'm just trying to pinpoint who's who and what is what. Okay, so I'm going to write the system on the next page. So we have A plus B plus C plus D plus E is 0, and -2D minus E is 0. Okay, and now we're going to solve this one. Okay, so if we are to do the matrix, right? So this is 1, 1, 1, 1, 1. There are 5 columns because there are 5 unknowns. And then we have just 2 equations, -2, -1, right? So each one A, B, C, D, E, right? So now we are looking at rank. Okay, first of all, as just M, which is the number of unknowns. Okay, which is the number of columns is 3, and then rank A. Okay, immediately I pop out that is 2. I'm just picking a 2 by 2 matrix that has right, non-zero determinant, for instance, this one. So it's 2, right? And immediately we deduce from here that there will be M minus K in this number of columns, 3. Where is my mind? Huh? It's 5, of course. All right, so its number of independent variables will be 5 minus 2, so it's 3. So it is number of independent variables. So immediately by the Buckingham, let's write this nice word again. Buckingham. Okay, pi theorem. Okay, we already know. Okay, we have that not hat. Okay, our relation, let's call it 1. So this is 1, okay. Can be expressed, okay, expressed. Okay, as a function of 3 non-dimensional variables. Let's call them pi 1, pi 2, pi 3, are adimensional, or non-dimensional is the same thing, variables given by combinations of the initial variables in in the initial relation 1, so combinations of h, tau, d, g, and b. Okay. All right, but the requirement of the problem is not just to apply Buckingham theorem plain vanilla, but actually to say what these pi1, pi2, pi3 are and end up with a relation that is this one here. Okay, so we need to end up here. Okay, somehow. You see d over h is adimensional, so that's a pi right there. But let's do the job. Okay, so what we have to do, we'll take the system and we're gonna solve it. So here, follow the double star. So from the system, okay, we're gonna solve it, and I need to choose like 3 independent variables. Let's see what I did in my notes. So I chose B, C, and D as independent variables. We can choose some others. It doesn't really make any difference in the result. Okay, so it's something that has the result is independent of this choice, because otherwise we would have a problem of consistency overall. So from here we can write the solution of this as, let's see how I put it nicely, A equals minus B plus C, okay, plus D. And then we have B, C, and D are whatever they want to be. So those are the independent variables, and E is minus 2D. So I repeat, you know, the way you solve the system, it doesn't really make any difference in the end result. So, hey, I lost the tablet. Okay. All right. Okay. Let's try again. I don't know where I'm losing the tablet. There you go. So the solution of this linear system is clear. Yeah. Okay. So what I was saying, so there are 3 independent variables. Here they are. Okay. So the span of solutions is a linear subspace over R5 that is 3-dimensional, right? It has 3 independent directions, right? All right. And what I was saying is that in solving this linear system, this double star system, it doesn't really make any difference which unknowns you're going to take them as independent variables. In other words, I chose B, C, and D because it's easy for me. You could choose A and E and D. Okay, you can choose any other 3. The end result will be the same, right? So it won't make any difference at the end, okay? Because the way to this theory is consistent. That's what I was saying. Okay, so I'm gonna write, so these are the independent variables. Okay, all right. So now what we have to do, I'm gonna flip the page, rewrite this, and then we're gonna make some choices for B, C, and D. Of course, I'm gonna choose one to be 1 and the other 2 0, and permutations, right? Because that's the easiest way to choose, and see if we get the result that we wanted. It might not work directly, but as I can see in my notes, it did work directly. Okay, so let's see. Okay, so we have A equals minus B plus C plus D. I'm writing again the solution. B, C, D are the independent variables, and E is minus 2D, okay? And remember, we had H at A, right? So F of, okay, let's write this one again, just to have it in front of us, huh? F of H tau, where is it? DGV equals 0. Okay, so we know that H at A, tau at B, D at C, G at, we have two D's in this question. Okay, so I'm gonna put a D hat on this one. Oh man, I didn't notice before. Okay, so the thickness, right? What is the distance in between the pieces? Let's call it the D hat, just to this, or a capital D. Let's make it a capital D everywhere. So we don't confund it with the D from the linear system because they're different objects. Okay, so D, there you go. D. D. Okay. This stays the same. Good. Okay, so the only thing that where it needs to be modified, it's here. So tau and D. Okay, so this would be the D as the distance in between the domino pieces. C, right? G at D, V at E will be adimensional, dimensional for A, B, C, D, E, S in, let's call this one 3 stars. Is here, okay? As in this wonderful 3 stars, okay? All right, so now, you know, I'm gonna, and we're gonna have 3 independent dimensional choices here, right? You know, as we have 3 independent variables in there, right? So I'm gonna choose now I'm gonna start 1, 0, 0, that kind of thing. B is 1 and C equals D equals 0. So we end up with H at minus 1. If you substitute, right? So if you substitute, then we end up with A being minus 1 and E will be 0. And so we get here that H at minus 1 tau at 1 would be the first dimensionless variables in this problem. So this is basically pi 1 will be tau over H. Okay, now we're going to do B 0, C is 1, D 0, and we end up with A being again minus 1, and D is 1. Okay, sorry. Yeah, okay, D is there, of course, okay. B, C, D, and E would be 0 again. So we end up with H at minus 1, D at 1 would be pi 2. So there you go, i.e. pi 2 is D over H, okay? And finally, we're going to do B equals C equals 0 and D is 1. And so A will be 1, and then we have E will be minus 2. So there you go. We end up with H at 1, G at 1, V at minus 2 will be the third non-dimensional variable. Or in other words, pi 3 will be Hg over V squared. Okay. All right, so we have, okay, we have pi 1, we have pi 2, and we have pi 3. And we know that f of pi 1, pi 2, pi 3 is 0, right? So f of h tau d g v equals 0 is, I'm going to call it reducible, because reducible, no, we don't spell it, I know how to spell it, is reducible, okay, to a relation of the form, okay. So that is, so now I'm going to put f in. So the first pi 1 was tau over h, d over h, right? That was, okay. And the last one, hg over v squared. Equals 0, okay. And now solve for hg over v squared. And again, I'm putting it in between quotes because it's, I'm making, I'm assuming that this implicit relation here can become explicit with respect to one of the variables. So we can explicitly express, right, something like hg over v squared equals some function f of tau over h d over h, okay. All right, so now solve for v squared. Why am I doing this? Remember what we had to choose to show, right? We wanted to show that v depends on root of gh and then some function of d over h and tau over h, right? I have to do something with the notation. Okay, so here is some function, some f, okay? So actually, to not confund it with the other one, we could put it f tilde or g or whatever, is some function, right? Okay, so coming back here, what we know we got to this gh over v squared equals some function of f of time over h and d over h. All right, so for v squared, okay, let's see where we get. So we're going to end up with v squared equals hg. Okay, let's do it. I don't want for you guys to think that I'm doing, I don't know what here. This is just plain vanilla kind of algebra. Okay, so in other words, v can be written as root of hg, and then would be 1 over f. And then here, I'm going to put here some g. So 1 over s, we're going to do g over tau over h, d over h for some function g. And that's what they wanted, okay? So in other words, right? The velocity depends on the root of the product of the height of the domino pieces and g. So now if we want to play, okay, if we want to play, would be something like this. So here I'm going to write this one. So it was like this. Some g function or some function g. Okay, we don't know what it is. Fine. Okay. So on the Earth, the gravity, the acceleration gravity on the Earth, let's say, is 9.8, right? So it's about 9.8 meter per second. So let's just take it 10. Okay. So, okay. All right. And let's say that I'm keeping the domino height, domino pieces height is the same. Okay, it's given, some given. Okay, all right, so that's the g. Okay, so now the gravity, the acceleration gravity on the moon is about is 6 times smaller than the one on the Earth. So it's basically 10 over 6 meter per second squared, if you want. Okay. So now the question is if V Earth is, let's say, 10 centimeters per second, okay? All right, what would be the same velocity on the moon? Without changing anything else, also tau and d, right? They're the same. So it's the same row of domino pieces that I'm lying down here, and then I take a bunch and I put them on the moon. So, you know, what will be the velocity on the moon? Well, you know, we will do something like this. So V, let's say V moon over V Earth, okay, would be root of H G moon over, and then times that function. We assume is not zero. If it's zero, it doesn't do anything. So this is G Earth. Yeah, okay. And then we do a little bit of back of the envelope algebra, right? Blah, blah. So we end up with a root of G moon over G Earth, okay? So anyhow, so it would be V Earth, okay, times root of, what did we say there? So it's 10, right? So it's 10 over 6, and then times 1 over 10. So it'd be V Earth times root 1 over 6. And actually, I did this. Why did I do the number? Oh, I didn't do it. Ah, okay, I did it. So this is about 0.4. Yeah, V Earth. So in other words, the velocity on the moon would be about 40%, if you want, of the velocity on the Earth. Okay, however you want to think about it. So if on the Earth is 10, right, there would be 4, right? So if the Earth is 10 centimeter per second, then on the moon will be 4 centimeter per second. Right? Yeah. There you go. And I have no idea how, you know, didn't do any mechanics of it, right? So it's just back of the envelope, right? Dimensional analysis. Okay, so that's what I had to tell you about these 3 problems. So you have 3 problems solved, okay? And well, I'll see you for office hours tomorrow if you want to come. Okay, bye-bye.